Let's begin. So we are starting the last section of our structure and bonding external. This question is going to be a calculation-based question. If you're good at math, this is a nice, easy excellence point. I'll show you guys when I'm doing some of these practice problems, how kind of points typically break down with this. With these calculations, we're thinking about energy, and we're thinking about if the reaction needs energy or if the reaction will release energy. So something we have to keep in mind is that chemical bonds store energy. So all chemical bonds store energy. Hopefully you guys have come across that idea before when you're thinking about different forms of energy, such as light energy, heat energy, kinetic energy. This is probably going to start a little bit like physics now. Chemical energy is what we see stored in our bonds. That is a potential form of energy. So we, for example, as organisms don't produce our own energy like plants do. So we need to get our chemistry from a food source. And we break apart that food source, and by breaking the bonds apart in our food, we then get energy so that way we can do our things. Some things to keep in mind is that when we break these bonds, we are going to need energy to do that. So breaking bonds absorbs energy. And then when we make bonds, we are releasing energy. Now, what we can do is we can compare and contrast then the energy that's required to break all the bonds versus the energy that is released when new bonds are made. So when I think about a typical chemical reaction, I have my reactants, and then I have my products. So in order to go from reactants to products, I need to break the bonds, which we know needs energy. And then products, we are making new bonds to form our new chemical compounds. So we are making bonds, and that's going to release energy. So what we can do is we can compare and contrast how much energy is needed versus how much energy is released to then figure out the energy change in a chemical reaction. So we call that change in energy enthalpy. And we annotate that as a delta H. So delta H equals, and then there's some number there. That tells me then how much energy is being absorbed or released. Are we okay so far? All right. So basically, there's two situations that we have. We can have a situation where the energy is being released or the energy is being absorbed. So just trying to see what that one is. There we go. All right. If my so if I'm comparing the energy of the reactants versus the energy of the products, and the product value is larger, so let's say I have a little graph. This is the reaction. That's the energy. So I have my reactants and energy, chemical reactions occur, and then there's my products, the reactants and products. So we see here how my products have more energy than my reactants. So what this tells me is that this is the amount of energy that was absorbed. So energy was absorbed from the system, and now it's being moved into my reactants, sorry, my products. Now, what we call this type of reaction is an endothermic reaction. And this, if we were touching the test tube, would feel cold. So like, for example, have you ever had one of those ice packs that like you snap something and then it's cold? That is an endothermic reaction. So whatever's happening with that chemical reaction, it's resulting in the absorption of heat energy. So what's really cool about this, cool, sorry, little pun. The thing you have to remember is that when things feel cold, they don't like transfer the cold to you. It's the loss of heat that's causing you to feel cold. And that loss of heat is because that chemical reaction is absorbing it. We could also have the reverse happen, where the reactants have more energy than the products. And again, I'll show you guys a little energy diagram because I find they're it's good to see it that way. So my reactants have a lot of energy, the chemical reaction occurs, and then I have my products over here. So in this case, we've lost energy from our chemical bonds, and that's been released to the environment. So that's energy released. So we call that type of reaction exothermic. The way I like to remember it is like exothermic, you are excited because now you're warm. Endothermic, I think of the end. It is cold and gloomy. This one feels hot. So basically you touch it and there's heat released. When you guys did the magnesium into the acid and then it started to bubble and release hydrogen gas, if you touch the test tube, it would feel hot. So that's an exothermic reaction. Questions, concerns, comments? All right. One thing I do want to mention is that you have to be careful when you're thinking. So if I'm thinking about if I'm thinking about water and the phase changes of water, if I'm going from a solid to, I should have grabbed a different color, liquid to gas, for example. So if I'm going from liquid to gas, we know that as boiling. Would that be an endothermic or exothermic reaction? If I'm boiling something. Exothermic. See, and this is what I'm talking about, how it's easy to get confused because you're thinking, oh, it's hot water because now the water's getting hot and it's like going into gas. But you have to think about it like, what are you doing? You are heating the water in order for it to become a gas. And so you need to put energy into the system. So if I was going from liquid to gas, this would be an endothermic reaction because we are absorbing that heat energy to boil it. The other way to think about it is that in order for me to go from a liquid to a gas, I need to break bonds or break intermolecular forces. And so that requires the input of energy. So that's why I like to use this as an example because it's very like contradictory to what you're thinking logically because you're like, oh, it's hot water, it's hot, it's exothermic. It's like, no, it's endothermic because in the system, it is absorbing heat energy. All right, if I was going reverse and I was going from liquid to solid, so I was freezing my water to make ice cubes, would that be endothermic or exothermic then? If you are freezing water to form ice. Again, it's contradictory because it's exothermic. Because you need to, wait, hold on. I'm trying to remember now. Yeah, exothermic. When we're going in the opposite direction. Because in this case, I want to make bonds. And by making the bonds, I'm going to be releasing energy. So if I am putting it into the freezer, I'm putting it into the freezer because I want the freezer to absorb the heat energy in order for it to go from liquid to solid. So that's what I'm saying. It's a little bit contradictory sometimes, but other times it'll be pretty obvious. So just keep that in mind when you're thinking about bond breaking and bond making. Every so often I have seen them ask a phase change question on the exam. And so you just have to think about it logically, what's happening at the molecular level. Are there bonds being broken? Are there bonds being made? All right. You okay so far? All right. Keep going. Okay. Can I move it? So let's talk about the calculations that you'll be doing for this topic. There are going to be a couple of different calculations. So we have the enthalpy calculations. You might hear me refer to them as energy change calculations. So this is going to fall into two different categories. The first category is going to look at bond calculations, and the second one is going to look at energy calculations. I'll start with the energy calculations. So with the energy calculations, these mathematical relationships are going to ask it in one of two ways. Either they're going to ask you, say for give an example, you've been given so many grams of something in a chemical reaction, or a volume of a solution, and they want you to convert it into telling me how much energy is going to be released or absorbed. So that's one way they do it. They can also ask this question in reverse, where they give you an energy value and they want you to work backwards and ask, okay, how much grams are going to be needed or created, or what's the volume of solution you need. And this is going to actually tie back to what we've done in titration, because you're going to be using that moles equals mass over molecular mass, or the concentration equation are the two that you might be using for that. So that's one set of equations one set of calculations you're going to be doing. The second type of calculation is the bond calculation. And what's going to happen is they'll give you the bonds energies for all the different bonds that are in a molecule. And they're going to ask you, okay, then what's the energy being released or absorbed? They'll basically ask you to find the delta H. The other version of this question is that they'll give you a missing bond, but they will give you the heat energy information, and basically they want you to figure out the missing bond value. So I'm actually going to break this topic into 3 lessons. We'll do this lesson here on bond calculations, and that's what I'm going to do today. And then we'll do a lesson on going from grams to energy, and then we'll do it in reverse, energy to grams. So there'll be 3 lessons to do that. We're just doing one of them today. Cool. All right, keep going. All right, so let me show you an example of what this will look like. So with the bond calculation one, what they're going to do is they'll give you a equation. Say, for example, methane gas that's burning to make carbon dioxide and water. So they'll give you the chemical equation. Most cases, they are pretty nice when it comes to the equations, and they'll actually draw it out so you know what the molecules look like. So you don't have to worry about doing the Lewis structure. So I'm just going to draw it in so you guys can see it. If they don't do this, I suggest you do this because you're going to need to count the number of bonds in both sides. So I've just translated the equation into what's going on at a bond kind of level. In theory, they should hopefully give this to you. If not, you're just going to rely on your Lewis structure knowledge. The other thing they will give you is they'll give you the value of all the different bonds. So they'll tell you that a carbon-hydrogen bond is 414 kilojoules per mole. they'll tell you that an oxygen double bond is 996 kilojoules per mole. So this will all be provided on the question. They'll tell you that a C double bond C bond is 804. And then the oxygen hydrogen bond is 463. So it'll give you all these values. And then what they're going to ask you to do is figure out the enthalpy, which is your delta H. That is your unknown. So let's see how we're going to solve that. All right, I'll just zoom out so you guys can see the whole thing. All right, so I'm going to split this reaction into two. I'm going to be thinking about my reactants, and I'm going to be thinking about my products, and then I'm going to compare those two numbers. So on my reactant side, I notice that I have a carbon with 4 carbon-hydrogen bonds. So I have CH, and I have 4 of them. So what that means is I'm going to take the 414 and multiply that by 4. So 414 times 4, I have 1,656. Cool. All right, the next thing I have on my reactant side is I can see that there is a oxygen-oxygen double bond, and I have 2 molecules of oxygen. So I have 2 bonds of those. So that would be 996 times 2. So I get 1992, and then I add those 2 values together. And so what that tells me is that on the reactant side, the amount of energy I need to put in to my reaction to get it going is that value there. Did I do that right? Okay. On the other side, I do the exact same thing, but with the molecules that are over there. I'm just trying to find another color. All right, so when I'm looking at this, I can see that I have a carbon and an oxygen, and they're double bonded, and I have 1, 2. So C double bond C times 2, so 804 times 2. So that's 1608. And then I look at my water, so the hydrogen oxygen. So I have 1, 2, 3, 4. Do you guys see how I got the 4? So each water molecule has 2 oxygen hydrogen bonds, and since I have 2 moles of that, I times it by 2 as well. So 2 times 2, 4. So then that's 463 times 4. That's 1852. And again, add them together. And we get 3460. And then my last step then is I want to take my reactant value and subtract away the product. So you do reactant minus product. So I would be doing that 3648 minus 3460. And I get my delta H equals positive 188 kilojoules per mole. All right, some things to keep in mind is what does the positive and the negative value mean? So positive tells me that it's endothermic. I need to input energy into the system. So if it's negative, then it's exothermic. It's releasing that energy. Some things to keep in mind for the achieved, merit, and excellence. For the achieved, you only need to get one of these two values correct. So you either get that number or this number, and that would be an achieved for this question. What that means then is I need you guys to show your work. So if you make a mistake and you just write down your final answer and I can't see the working, I don't know where that mistake happened. So that's the achieved. The merit is getting this number. And then the excellence, which is really ridiculous, and I highly disagree with it, but it is what it is that you need to have 3 sig figs, the 3 significant figures, and that is 1, 2, 3, so that one's fine. And we need the units. So that's all you need for the excellence then. So it's a really annoying kind of distinction between the merit and excellence is just, do you remember your significant figures and your units? All right, questions, concerns, comments? All right, I'm just mindful about how long I've talked, and I want to give you guys a chance just to have a break in practice. Are there any questions? No? Can I move it? Okay. So what I want you guys to now do, we'll have a little break, and I want you to do SciPad pages 108 to 109. If you want, you can skip the beginning theory questions and go straight into the calculations. I just want you guys to have a chance just to practice some of the math. And then towards the end of the lesson, I'll show you guys how to do the other version of this question. Cool? All right. There was a small error when I was copying my notes down. The oxygen double bond is not 966. It is 498. Yeah. So that number then changes to 498, and that number changes, oopsie, 498 times 2. Yeah, that's where I got the mistake from, where I got the 996. I was pulling the wrong number. If they gave you the wrong number on the assessment, then they obviously would be not marking you incorrect on that. That was a transcription error from somewhere else. Yeah, I knew something looked funny. Yeah. All right, I was wrong. So that should be negative 808. And since it's a negative number, negative tells us exothermic. And I can add that to the beginning notes as well. So the delta H would be a positive number. And this one, the delta H, whoopsie, delta H would be a negative number. You guys need me to get anything else on the piece of paper? Did I massively confuse you? Okay. Did I? Okay. Do you want me to backtrack? Okay. All I did was that I made a mistake with this number when I copied it down, and then that error carried through. So what I'm doing is I'm just changing the number so that way it's right. Yeah. And then this changes that number to a negative number, which means it's actually an exothermic reaction, which is what I thought was supposed to happen anyway, because it's burning methane. Methane's supposed to be hot. And then the other thing I just added was this extra note that enthalpy, if it's a positive number, it's endothermic, and if it's a negative number, it's exothermic. Yeah, it's a good way to double check your work. Recording, it just like jumped multiple seconds. All right. Cool. Last bit of notes for the day. I just need to show you what happens if they ask this question in a slightly different way. I want you guys to be ready for it. All right. Gentlemen, Ready? Okay. So there is another way they could ask this question, and this is what I like to call the unknown bond question. So in the examples that you guys have been doing, they have given you all the bond energies, and they ask you to find the enthalpy. In this example, they won't give you one of them, and you have to figure that out, but they will give you enthalpy. So let me show you what I mean. So let's say they have methane, and you are reacting it with ammonia, and you are forming this CNH and 3 hydrogens. You need me? Okay. So hopefully they're nice and they give you the structures to all these molecules. Otherwise, you have to use your Lewis structure information. They should, in theory, give you the drawings of all these molecules because it's not fair to ask that question twice. So let me draw it out so you guys can see them. So it'd be that guy. It would be this guy. This one would be C triple bond N, and then I just gotta double check where the H is attached to. Just gonna have to quickly Google that. Pretty sure the H is attached to the C. Yes, it is. Sorry, squished it. And we have the hydrogen. Now remember, there is a 3 in front, so we actually have 3 hydrogen molecules like that. I personally like to draw them all out so I know, like, visually that I can count everybody. I say that is a useful kind of thing to do because if you make a mistake with the number of bonds, it's going to not drop your answer from an excellence to a merit. It's going to drop it from an excellence down to an achieved. Because remember, the merit level is getting the right number. So it's a big drop if you make a mistake in your calculations with just something simple like that. So do watch out for it. All right. So in this example, they have given you the bond energies for the carbon to hydrogen, 414. They have given you the C triple bond N, and that one is, where did I find my number? 860. They give you the hydrogen, which is 436, and they give you the delta H. They say the delta H value is, where are you, delta H? Positive 247. So this is all the information that they've given you, and they want you to figure out what the NH bond is. That's your question mark. So you see how this question's set up slightly different than the last one? Last one, they gave you all the bond energies, and they asked you to find the H. In this case, they've given you these 3, the enthalpy, but they've missed out on one of the bonds, thus the unknown bond that you're calculating for. All right. Setup is more or less the same. So do the same sort of working. I have my CH, and I count that there's 1, 2, 3, 4. So I'm multiplying that by 4. So 414 times 4. You are allowed a calculator on the assessment, so don't forget your calculators on the day of the exam. So that's that one. The nitrogen hydrogen bonds, I can see that I have 1, 2, 3, so it's times 3, but unfortunately I don't know what the value of that is. That is what I'm solving for. So that's my little question mark. So I'm going to represent the fact that this is unknown as an X, just like you do in algebra. So what I have here is actually 3X, because that is my unknown. Are we okay so far? Okay. So if I was just going to write this down as a summary, because I don't know that number, this side would be 1,656 plus 3x. That's what I'm going to use for that side. On my product side, I have a C triple bond N. I only have one of them, so that's 860. I have a C single bond H, only one of them. That's 4, 1, 4. And then I have a HH. I have 1, 2, 3 of them. So I times that by 3. So that's 436 times 3. So that's 1308. And then we add all those numbers together. So on this side, I have 2582. All right. We okay with that? Show you're working, because again, a lot of the achieved points is getting one of these two correct. So basically you have 2 shots to get the achieved. All right, last thing I do is then setting it up and using the numbers that I had. So we know that we're doing reactants minus products. So I'm going to do 1656 plus 3x. I'm going to subtract my products. So that's 2582. And then I'm going to set it equal to my enthalpy, which I do know. I know that from up here, it is 247. And then I just do the math to cancel everybody out. So I can put these two numbers together. I would have 3x minus, because I know that's going to be negative, 926. I add the 926 to both sides. So that cancels out. And I have 3x equals 247 plus 926. That is 1173. And then I just need to divide by 3. And I have x equals 391. So what that tells me is that the nitrogen-hydrogen bond is equal to 391 kilojoules per mole. Again, 3 sig figs units. The number you get here should always be a positive number as well. Just keep that in mind. The reason why is because when we're talking about bond energy, all of those are referring to as positive numbers because it's the energy input to break the bond. All right, questions, concerns, comments? No? All right, do I need to leave that up? I see pens going. All right, just to keep in mind, follow-up work for this lesson. If you're feeling confident, if you're not feeling confident, I recommend SciPad pages 105 to 109. If you want, you can primarily focus on the calculation component to it because usually on the exam, there isn't like a write-up theory to it. It's just the math. If you are feeling confident, you can start on the no-brain too small questions. Just skip through to the calculations for the bonds. We haven't done the other version yet, but we'll do that next lesson.